Hi folks, welcome to Quantum Tunneling with your host Russ Case. A guy who likes physics and is good at solving problems. Now, quantum tunneling is an interesting effect that has a huge impact on our lives. It allows us to understand everything from the transistors which power computers to the flash storage that we store our favorite anime movies on. It even helps us understand how the sun's fusion works. But what I'm going to focus on today is how quantum tunneling helps us understand alpha particle radiation. First, let's go back to classical physics. In classical physics, all matter has energy. Part of that energy is potential energy, like, say, the top of this mountain. Some of it is kinetic energy, like the kinetic energy that this car has down here. Now, if this car doesn't have enough potential energy, it's not going to be able to cross over this mountain. In fact, it's probably just going to end up stuck down here. What we have to do is put gasoline into it, get enough speed or enough energy in total just to get us over top. We'd never expect that it would just roll its way up and over by itself. Another example we can think of is this marble. Let's say you put a marble into a cup. What would you expect that marble to do? Probably just sit there. What if I told you that your marble teleported outside of that cup, rolled away, and fell off the table? You'd probably say that's pretty crazy. But in a sense, that's sort of what we see with quantum tunneling. Now, the same thing applies to the nucleus of an atom. In the early 20th century, alpha radiation confounded scientists. Alpha radiation is characterized by the escape of a particle formed by two neutrons and two protons. Now, that isn't so weird until you realize that the forces working to keep that particle in the nucleus are actually far stronger than the energy that the particle has. And we really can't explain with classical mechanisms why that particle flies out of the nucleus. In fact, Ernest Rutherford submitted a paper in 1927 showing that in experiments, uranium-238 emitted alpha particles which were less than 1/2 the expected energy. In response to this paper, this fellow, George Gamow, a Russian scientist, proposed a theory of quantum tunneling. This theory suggests that when a particle's wave packet encounters a potential barrier, its probability of being anywhere inside that barrier and beyond it does not necessarily drop to zero. Instead, in accordance with Maxwell's equations, the particle's wave function potential drops exponentially with distance, as we see here. But it never approaches zero. In fact, if the barrier is short enough, it can reappear on the other side with a diminished amplitude. Now, the result is that the wave function remains continuous and smoothly drops towards zero, and that allows for the very, very, very rare occurrence of a particle simply appearing on the other side of a barrier at a diminished energy level. Gamow was able to actually calculate a relationship between the half-life of an element and the energy of its emitted particles in radioactive decay. For example, here we have polonium-214 with a particle energy of 7.7 mega electron volts and a half-life of just 160 microseconds. If we look down here, we have uranium-238 with an energy level of 4.18 mega electron volts and a corresponding half-life of 4.5 billion years. Now that's pretty huge because right away we're taking this quantum theory and applying it to real-world applications. This is actually happening, people. Now, these two fellows, Ronald Gurney and Edward Condon, they were unfortunate and submitted a paper on the exact same thing the day after Gamow, but I will give him credit for this great quote. disintegration is a natural consequence of the laws of quantum mechanics without any special hypothesis. I think that's a really fantastic way to look at this. Quantum tunneling gives us a real interesting view into what exactly is going on at the atomic level. And not only that, but it helps us do some really cool stuff. Anyways, that's me, signing off. Thanks.